This video will cover section 8.3, matrix operations and their applications. Okay, so we just got done reading the introduction, which talks about certain places where you can find matrices, such as a computer or any digital device. And so if we talk about pictures, for example, any picture that is a black and white picture, every picture has this thing called pixels, right? Mm-hmm. And so the better quality of your camera, the more pixels you have. And so each little pixel there is a number. And so if you have a black and white picture, the color black, I believe, and let me just look at this. So sorry about that. Black is going to be the number 0, and then white is going to be represented by the number 255. So you have a total of 256 color combination. So you have all shades of gray, not only 50. You have what? 254. 54, yeah, because you have white and you have black. Yeah. Yes. So then the numbers, if it's a black and white picture, is very simple. If you have a color picture, every single pixel is a combination of 3 digits. And those 3 digits come from the RGB combination of colors. Red, green, and blue. Very good. And so, for example, if you just want, let's say you just want like pure green, then you will put a 255 here and then 0, 0 here. Okay? Oh. So that's how and you can actually Google those, and after the college class is over, we're going to do a little bit of coding, programming, where we use this really cool devices that have to create lights. In one training, I made like a rear view camera that your cars have. So I programmed it so that the lights will change, like red, green, yellow. Okay, so anyways, so please don't ask me, how can we use matrices in real life? Because you're actually using them already. If you are using Photoshop or Instagram or any type of filter that I know all of you use, you are already using matrices, whether you like it or not. In fact, facial recognition was possible due to matrices. And so the basis of that is that they detect the sudden changes in color. And they check horizontally, they check vertically, and they check diagonally. And that's how, it's not magic, it's actually math. That's how, when you upload a picture, your phone knows who is that person. Okay, so anyways, let's just move on to this one here. Well, before that, every matrix has a thing called dimension. And that's the same as the order. Okay? And so if we look at the matrix here, we have 2 rows, 1 and 2, 2 rows, and how many columns? 3 columns. So we're always going to number the rows first. So the order of matrix A is 2 by 3. It's not 2 times 3, we just say 2 by 3. Okay, now by the way, we're going to use uppercase letters to denote matrices. And the lowercase will be reserved for the elements of that particular matrix, which will be the entries inside that matrix. So the subscript for I, it indicates the row number. And the subscript J indicates the column number. So for part B here, the question is if A is that matrix that we have here, and all the elements could be denoted as such as that, the element A, 2, 3, and that means second row, It's not A23, it's A23. Second row, third column. So if you look at that, that will be second row, third column. So that will be equal to negative 1/5. Now let's look at the other one, which is here. Identify element 1, 2. So that's going to be first row. Remember, the row always first. Second column. So first row, second column, that would be 2. Here. Do we have a question here? No, right? So dimensions, how big is your matrix? First you have to name the row, then the columns. Okay, so let's go to your last page. And look at your second to last slide. And so we'll come back to it, but just quickly to show you what I was talking about. Of course, here the colors are different. Remember, in the real world, black is actually 0. And white is 255, okay? And all the grays are here. So for this one, we're going to use this particular ones where 0 is white, 1 is light gray, 2 is dark gray, and 3 is black. And so I know your copy might look like this is either black or dark gray, but it is dark gray, okay? So if I want to write down a matrix that represents each pixel, it will be, first of all, is what are the dimensions or the order of this matrix? 3 by 3, very good. And so the first column is going to have the number, what digit, to represent dark gray? 2. So 2, 2, 2. And then we have another 2 here, right? Because it looks like an L shape. And the rest of the entries are going to be light gray, which is represented with the number 1. 1, 1, 1. Okay? And so that is what I mean by each pixel is a number. We'll come back to this one to answer part B, but not yet. So let's go back to the second slide. Okay, so we have a little statement here, so let's write it down. Two matrices are equal if and only if, remember this is the double arrow. Like if one way is true, the other way must be true as well. If and only if every element, remember every little number inside or variable, every element with the same location or the address must be equal. And so if we make a statement like, and well, before I do that, if we are comparing two matrices, let's call them A and B, those two matrices will be equal if and only if, first of all, they have to have the same dimensions, right? But also, for every single element, remember here, the I and the J is just to generalize the number of row and column. So here, this is all the rows. For all the rows and for all the columns, every single element with the same row and column will be equal. So here, the question is saying, well, the example is saying, if A and B are equal, that is only because if and only if whatever is in first column, first row, first column will be equivalent. So X equals 1. And then we have second row, first column, so Z equals to 3. We will also have Y plus 1 is equal to 5. And if we want to solve for Y, that's pretty easy. It's just 5 minus 1. So y equals to 4. And then we have one left. It's just pretty easy, right? 6 equals to 6. And we don't have anything to do there. That was just there. So yes. So you could say it both ways. If all the elements are the same, then the matrices are the same. If the matrices are the same, that's because all the elements with the same address are the same. Okay, so next thing, we have here addition, subtraction. It's very simple. This is the long way. So just like the video was telling you, you add the numbers that have the same address. So that's what we have here, written the long way. 1 plus -1. Just like we have that, we could also have -2 plus 6, and that's what we see here. Yeah, are we okay with that? So let's just do the examples. Okay, so in this case, I'm going to just write the long way, but so 0 plus -2, and then, so we got that with that, and then now 5 plus 3, and then the next one will be 3 plus 5, and then -2 plus 7, 6 plus -9, and then -8 plus 6. And then, of course, we do have to write the answer. So 0 plus -2 is -2, 5 plus 3 is 8, 3 plus 5 is 8, -2 plus 7 is positive 5, actually. 6 plus -9 is -3, -8 plus 6 is -2. And we're done with that. Do we have a question about addition? So, what is the first thing you have to check for? Dimensions. Very good. Very good. Let me give you your card. So the next one, we're subtracting now. And so we'll have -6 minus -5. So that will be 6 plus -6 plus 5. Then we'll have 7 minus 6. And of course, this could be doable, right? It is doable. 2 by 2, 2 by 2. So they have to have the exact dimension. We want to add or subtract, like Andrew said. So 2 minus 0. And then -3 minus -4. So plus 4, right? Because it's minus -4. I mean, you can write it that way too, if you want to be more cautious about your signs. Then we perform the operation. So -6 plus 5, -1. 7 minus 6 is 1. 2 minus 0 is 2. -3 plus 4 is 1. Yeah? Is that okay? Okay. Sometimes it doesn't seem like it. All right. So addition, subtraction, very easy. Let's move on to, okay. So a zero matrix is a matrix where all its elements are equal to 0. And we also call it the additive identity. And what we mean by that is that if we add any matrix, such as the matrix A, to the matrix B, which is the zero matrix, you will obtain the same original matrix that you had before. So very easy to demonstrate. -5 plus 0, and then 2 plus 0, 3 plus 0, and 6 plus 0. And so of course you get the original matrix. -5, 3, 2, and 6. So we do have something called additive identity. And then we have another thing that we're gonna go over on Wednesday, which is called the multiplicative identity. Do any of you remember what it is? Like from algebra 2? For a card, maybe.
What's the multiplicative?
When we talk about matrices. Which one? Oh, that would be the inverse. To find the inverse, yes. Easier than that. Think easier. Yes. Well, yes, it's gonna be like when you get the same result at the end. But what is would it be just once? It has, okay, I'll give you like a hint. It has ones and zeros, but where?
Oh,
the one is in the middle.
The diagonal has ones.
And the rest have zeros.
my God. My God.
Right. So you guys, the multiplicative, back over here, please. The multiplicative update identity is the one that looks like that. Oops, using one here. So this is the main diagonal. But don't worry, we'll revisit that on Wednesday. So anyways, all the properties that apply to addition with real numbers also apply to addition of matrices. So matrices are commutative with respect to addition, meaning that A plus B is the same as B plus A. Like 2 plus 3 is the same as 3 plus 2.
2 plus
right?
2 is 4.
So it is also associative, so you could associate or group these two first, add them, and then add them to the third one. Or you could add the second and third, and then add that to the first. So please write that down on your paper. And they're also, well, we have the identity, additive identity, which is the zero matrix. And of course, since addition is commutative, adding the zero matrix second or first, you will get the same result. And the last one, it talks about the additive inverse. That's what you were talking about, Amy, kind of. So if you add a matrix times its additive inverse, or in other words, its opposite, all the elements with the opposite sign, then what are you going to get? 0.
Wait, wasn't that Shelby who said that?
Was it you, Shelby?
Yes.
Okay, Shelby. You take the credit. Okay. Now let's move on to scalar multiplication. And so make sure you guys copy this part, please. Okay, so the next one, we have what is called a scalar. Okay, could you guys stop talking, please, before I ask you to exit the room? We have time for this. So what you're going to do is distribute that number. So that number outside, think of it as a number outside the parentheses. What do? You distribute that number to everything inside the parentheses. Say that again?
Can you say it's like 4?
Well, not really, because this is only one number. It's just think more like distribution. Yes. So in this case, we will have 4 times 2 is 8, 4 times 5 is 20, 4 times negative 3 is negative 12, and 4 times 0 is 0. Okay. And that is what is here, scalar multiplication. So that we have the formal definition. So you have a matrix multiplied by a number, let's call it C. Then every single, for all elements in the matrix, for all I from 0, not from 0, sorry, from 1, from row 1 to what will be the last row of this matrix? So read what it says right below definition of scalar multiplication. So how many rows does that matrix have? Nope. Nope. The answer is a letter.
Oh.
A letter. And-
Oh.
Nope.
Put in a G.
What? Okay, so right here, you guys need to get used to reading, you know?
No, it's
The answer is here. I'm talking. If A is this matrix of order m times n, it means that it has m rows. How many columns does it have? So for all j from 1, 2, 3, all the way to n. That's what it means. So when you do that, you have to multiply, distribute the scalar to every element. That's pretty much it. Okay, next one, we could combine addition and scalar multiplication. So in this case, we're going to have matrix A multiplied by 3, and then matrix B multiplied, matrix A multiplied by 2, matrix B multiplied by 3. So 2 times A, that will be 2 times -1 is -2. 2 times 4 is 8. 2 times 3 is 6. And 2 times 0 is 0. Then we will move on to matrix B. So 3 times 2 is 6. 3 times -3 is -9. 3 times 5 is 15. And 3 times -6 is -18. Now, if you add those two matrices, you get 4, -1. Let me know if I make a mistake, because it's very likely. Okay? No? Which one?
Oh,
yeah.
Okay.
You're right.
So now let's do, just for fun, let's finish part A. That was super easy. So you guys go ahead and do that, please. And then I'll write my answer. So you're going to distribute, and the scalar is negative. That's fine. The scalar, wow, I can really make something think. The scalar,
Wait.
the scalar can actually be positive or negative, and it could also be a fraction. Okay? So go ahead and distribute -5 to all the entries here in matrix B. Make sure you do it to the correct matrix.
Do we write things?
No. Okay. So check with me, please. I get something wrong with me now. So -5 times -3, that would be positive 30. -5 times 5, -25, -10, positive 30. Yes? Do you all agree?
yes.
Yeah, I think so. Okay. Now let's talk about the properties for that, for scalar multiplication. So all the properties that apply to real numbers also apply to that, to make it scalar multiplication. So it is associative. Here we can multiply two scalars first and then times the matrix. Or you could choose to do to multiply one scalar times the matrix and then times the other scalar. So please write that down. And then we have the scalar identity. It's just the number 1. But the identity matrix is the one with the ones across the diagonal. We have distributive property and another distributive property. These are very similar, but here what you're distributing is the scalars. Where here what you're distributing is the matrix. So that's why they're a little different. Okay? So please copy all of that.
What happens if you have a scalar of 0?
Then your multiplication will give you the 0 matrix.
Oh.
Yeah. So we try not to use those. Actually, let me see how they define scalar by splitting 0. No, it's just a real number. Let me see. Yeah, it's just a real number, so it could be 0. You will just get the 0 matrix. Okay, guys, so you could solve an equation with matrices, and you will have a problem like this on your test. Sometimes people skip it because they think it's too difficult, but it's not. So make sure that you look at your notes when you are solving your take-home exam, which you will get on Wednesday, probably. Maybe Friday. I just want to make sure that you know this. So this week we're covering our last 3 sections. 8.3, I'll just write it here. So 8.3 and 8.4, they both have homework. And this homework is going to be due on Friday. And I will leave it open until 10 p.m. But that's when it's due. I'm not going to reopen it. I'm not going to give extensions. Nothing. Nothing. Like, at all. I don't have time for that. I need to finish my grades. 8.5, no homework. Okay? But there's going to be one problem on the take-home. Now, why am I making the homework due on Friday? Because I know how you guys procrastinate. And if I make it due on Wednesday, you're not going to do your homework. You just won't. You're going to procrastinate, and then the take-home exam will pile up on you as well as the final exam. So my goal is that you finish your homework by Friday, you dedicate your weekend to the take-home exam, and then after that, you study for your final. And that's it. The final will be given Friday if I have it ready Wednesday, but more than likely Friday. Okay? And then it will be due Monday, because I have to grade them all so that you guys can have it back. Yeah, hopefully.
Are they paper exams? Or?
Yes, they're going to be on paper. And since it is take home, I'm going to be very picky about you showing your work, not skipping steps at all. All right, going back to this problem. Make sure you look at your notes if you see one like this, which is very likely. So what you do, let's think about this as an equation, just regular equation. How will we solve it? Well, you all know, first we say B, what do we do with plus A? Subtract, so minus A. And then we know that to get rid of that 2, we have to divide by 2. Or in other words, remember, with matrices, we don't have division, but we do have multiplication by a scalar. So this will be, divide by 1/2 is the same, divide by 2 is the same as multiplying by 1/2. So make sure you don't leave that problem unanswered on your test, please. So now let's do what we're saying here about with the matrices. So we're going to have that matrix X is going to equal to 1/2. And then let's just write down our matrices first. So first we need matrix B. That actually matters a lot. And then we're going to subtract matrix A, which is 1, -5, 0, and 2. So matrix X will be 1/2 times, and here I'm just going to write the matrix as a subtraction. So -6 minus 1, and then 5 minus -5, so plus 5, very good. And then we have 9 minus 0. And then we have 1 minus 2. So now we're here. -6 minus 1 is -7. 5 plus 5 is 10. 9 minus 0 is 9. 1 minus 2 is -1. If you guys notice I make a mistake, let me know, okay? And now, what is left for us to do? Multiply, distribute, very good. So 1/2 times -7, that would be -7 halves. 1/2 times 10 is 10 halves. 9 times 1/2 is 9 halves. And then -1 times 1/2 is -1 half. Now, if there are numbers that can be simplified into integers, do it. Like, for example, here, 10/2, 5. The rest, just leave them as improper fractions. So we do not want mixed fractions, and most of the time we don't want decimals. Do we have a question? So here the answer for x was a matrix, not just one number. No questions? No? Okay. Right, now multiplication of two matrices. And so what they were saying, I like that, the way they were setting them up. So we'll try to do that as well. Sometimes this is a little confusing, so you could always think of, well, first of all, you have to make sure that the dimensions, they work. So we're going to look at this again on the next slide, but just to remind you, the number here has to match this number. The two in the middle must be equal. If they're equal, then the product is possible. And what will be the dimensions of the new product? The numbers that you see on the outside. So this is going to be a 2 by 2. So for example, here, this is first row, first column. First row, second column. Second row, first column. Second row, second column. So when you multiply, you're going to be taking, for this one here, is going to come from first row, first column. And so that's going to be A times E plus B times G. Then for this one here, we're going to take the first row. So what does it say here? Second column. So that's going to be A times F plus B times H. So let me move this so you guys can copy that with letters. Go ahead and copy that part. Okay, so go ahead and copy that statement. And for the product to be defined, these two numbers must be equal. And the resulting matrix will have an M like. And in case you did not check your answer, that is the answer for the multiplication. Okay, continuing with example 6. Sorry if I ruined your Thanksgiving. Let's see, we're going to multiply two matrices A and B. First, we're going to multiply A times B, and then second, we will multiply B times A. So if you notice, matrix A, the dimensions for it will be 1 row, 3 columns, so 1 by 3. And matrix B is 3 row, 1 column. So if we are going to multiply A times B, I'm going to position them first. So A goes here, 1, 2, and 3. And then matrix B will go here. And that is 4, 5, and 6. So this is a 1 row, 3 columns. And this is 3 columns, 3 rows, 1 column. So the two numbers in the middle, they match, right? So, but what is the resulting matrix going to be? It looks kind of weird, right? 1 by 1, yes. So what does that mean?
It's gonna be one.
Just one number right here. 1 row, 1 column. We'll find the answer in a minute. Now let's look at the other one, and the other one says B times A. So let's position the two matrices first. So matrix B, it is 4, 5, and 6, and matrix A is 1, 2, 3. So let's see if this is possible. This is 3 rows by 1 column, and this is 1 row by 3 columns. So can we multiply this one? Yes. because the numbers in the middle match. But the resultant matrix is going to be a pretty big one, right? What are the dimensions going to be? 3 by 3. So the numbers on the outside. Okay, so you can see it's pretty obvious, right, that AB does not equal BA. I don't even need to know what the numbers are because the dimensions are different, so it's pretty obvious. They will not be equal. So this is one thing of caution. Matrix multiplication is not commutative. Okay? That's very important. Okay, so let's multiply here. So we're going to take first row times first column, and that's it. But how are we going to get only one number out of those?
Yeah, I want to get it.
Add them all together. Very good. So 1 times 4 is 4. And then 2 times 5, 10. And then 3 times 6, 18. So this one is just going to be the number, what? 32? 32. And that's it. That's a 1 by 1 matrix. Okay, now let's do the other one. So the other one, we know we're going to have 3 by 3, right? Okay. So this is first row, first column. So this is the only entry from the first row, and this is the only entry from the first column. That's it. There's nothing else we add. So 4 times 1, 4. Then here we need first row, second column. So first row, second column. 4 times 2, 8. And then we need first row, third column. So that's first row, third column. 4 times 3, 12. All right, you guys do the rest. So here you need second row and then every element from there. And then the final one will be third row times every column. So try it on your own and then I'll write the answers. So we have our answers there. Do we all agree? Yeah? Okay. Now, yes.
Did you put 15 on the last one?
Yeah.
Oh, that's 18, right? Okay. I was testing you guys. So, here, Carlo, you get a card.
And just so upset.
Okay, so, if you notice, for example 7, we have the same matrices, but they are positioned in different order, right? So, let's see if this is possible first. So, this here we have a 2 by 2, and here we have a what? How many rows? 2 by 4. Could we multiply here? Yes, because these two are equal. So our resulting matrix, what is it going to have? 2 by 4. Okay, now let's look at the part B. So here we have 2 rows by how many columns? 4 columns. And here we have a 2 by 2. Can we multiply here?
No.
No, because those two numbers are not equal. So this product is undefined.
Yes.
You could have something like that on your test. Hopefully. So let's multiply. So we have first row, first column. 4 times 1 is 4. 2 times 0, 0. Then we move on to first row, second column. 4 times 2, 8. 2 times 2, 4. Then we move on to first row. Which column? Third column. So 4 times 3, 12. 2 times -1, -2. Then we move on to first row, fourth column. So 4 times 4, 16. 2 times 6, 12. And now we're done with all the first row, so it's time to go to second row, and then we work our way down times the columns. So if you guys could please do that on your own. While I start adding my numbers from here. My first row. So I'll finish first row, you guys finish second row. You could talk to your partner if you need. So second row, first column. You gotta try it because when I do it, it looks very easy.
First row, second row, second column.
So second row, first column, second row, second column. Second row, third column, second row, fourth column. So the address of each entry tells you what to do. So look, Amy, right here, you're gonna need second row, second column.
Oh, okay.
So let's do second row, first column. So 1 times 1, 1. 3 times 0, 0. Then we move on to second column. 1 times 2 is 2. 3 times 2, 6. Now you guys finish the last three. Come on. You have to try it. Because when you do it, when you try to do it on your own, it's not as easy as it looks until you get like a good rhythm. Okay, so the last two entries, where are they?
0 and 14. 0 and 22.
0 and what?
22. Yep.
No?
Yes.
Do we all agree?
Yes. Agreed.
No, now I'm counting. 3 minus 3, okay, that's 0. And then 4 plus 18, 22. Very good. Do you guys remember doing this in algebra 2?
Yes.
Not this, but I remember when teacher said.
Yes, we did a little bit. Okay, of course, all those properties are, they also hold, they're true, I'm still talking. However, the only one that we don't count here for matrix multiplication is not what? Commutative. Like AB does not equal BA. Okay, now let's answer question part B to this one. And so we already have the matrix, remember? The light gray, and dark gray. So what we're going to do here is increase the contrast. So what does that mean? It means that the dark gray will get darker. So it's going to go to black. And then the light gray will go to what? Will get lighter, actually. So it's going to go to white. That's how you increase the contrast. The darker gets darker, the light gets lighter. Yeah, kind of. Okay, so let's see. We have the following matrix. We already know what it is. We did that at the beginning. And so we need to find something here that will give us the following. We want the L to be black. And the color black is represented by number 3. And then we want the light gray to look white. And white is represented by 0. So what do you need to do to the 2s here?
Add 1.
Add 1, right? So we're gonna put 1, 1, 1, 1. And then what do we need to do to the 1s to be 0s? Subtract or add a -1. And we're done.
Yes.
Well, we have one more slide. Sorry. But this one is pretty easy. So have you guys logged in to my math lab at least? Open my math lab. Log in. While I'm going over this. Okay, so I don't know if you recall from the video, there was a thing called linear algebra. And so linear algebra is a class engineers have to take, computer scientists have to take. And so you learn to do several things with matrices. And you kind of start from solving systems, like we did in section 8.1. And then from there, there's a section called 8.3. I'm sorry, 8.2. We're doing 8.3. 8.2 is about systems that are inconsistent and or dependent. So just as a review, when we talk about systems that are inconsistent, what does that mean?
Not consistent.
Well, of course, they're not consistent. So what does that mean?
They are grammatical.
They're what?
They don't follow a pattern.
Pattern. We're not talking about patterns at
They
all.
don't.
Huh? They don't have a solution. That's correct. So inconsistent systems have no solution. What about dependent systems? Dependent, infinitely many, very good. All of your part. So this is no solution, and this is infinitely many. Okay. So who's taking physics?
I think I'll.
Okay, most of you. You know this little thing called vectors, right? You all love them. So in matrices, with matrices, we can look at systems as an equation if we look at the rows horizontally. But if we look at them vertically, they are vectors. And in real life, not in real life, in math, you can have vectors that are like 2 by 2, 3 by 3. For example, if I want the coordinates x, y, z, it would be like 2, 2, 1, something like that. Then if I have another vector that is, for example, 4, 4, 2, and then let's say I want another one that is 1, 1, 1/2. And I put them in a system, what do you guys think I will get? Would I get a solution? Would I get one solution, infinitely many solutions?
Well, I think we can solve it. It's just gonna take a lot of work.
Well, would you guys say that this vector, let's call this as vector b. This one is actually going to be 2 times b. And this is actually 1/2 b. So if I put them all together and I make a system of equations, I'm going to get a dependent system which will have infinitely many solutions. Okay? So all these things with like numbers, math, physics, matrices, they all start kind of like coming up together. And I'm very sorry that some of you will never get to see that, but for those of you, you will remember that. And it's actually pretty cool when that happens. So what we're going to do with this one is use those vectors. So if you notice here we have x coordinate as the first row, y coordinate as the second row. So if we plot those points like -2, -3 here, and if I connect it like that, that reminds you of a vector, right? Yeah? Okay. So for now, just plot the points. -2, -3, and then you will have -1, 2. And then we have 3, 4. And then we have 1, -2. Okay, so for part A, and we already have the original shape here. So for part A, we're going to move the quadrilateral 4 units to the right. So we have the matrix here that represents the shape or the quadrilateral. And then we want all the x coordinates. So remember, x coordinates is the first row. We want them to be shifted 4 units to the right. So we're going to add, what should we add? 4. We're just going to add 4 to the first row. Because the first row is the x coordinates. Now we want the y coordinates to be shifted 1 unit down, so we're going to add -1. Very good. So then the resulting matrix will be -2 plus 4, that will be 2, 3, 7, 5, and on the bottom we'll have -4, 1, 3, and -3. So let's plot them quickly. So vertically, okay guys? So it's like 2 comma -4. 2 comma -4. And then 3, 1, 7, 3, and then 5, -3. Okay. All right, part B, it says shrink the perimeter by half. So what I'm going to do is just multiply the whole matrix times 1/2. So we get -1, -1/2, 3 halves, 1/2, -3 halves, 1, 2, and -1. So -1, -3 halves is here, -1/2 and 1 is here. 3 halves, that's 1.5 for the x, and for the y, we get 2. And the last one, 1/2, -1. Okay. And that is the perimeter shrink by half. Okay, and then the very last one, we're going to multiply BA so matrix A is -2, -3, -1, 2, 3, 4, 1, -2. So remember, this is a 2 by 2 and this is a 2 by 4. Can we multiply it?
Yes.
Yes. Maybe you didn't want to, but yes, we can. And the resulting matrix will be a 2 by 4. Okay. So first row, first column, -1 times -2 is +2, 0 times -3 is 0. And then second column, -1 times -1 is +1, 0 times 2 is 0. And then -1 times 3 plus 0. -1 times 1, -1 plus 0. So my first row will be 2, 1, -3, and -1. Second row, first column, so that will be 0 minus 3, 0 plus 2, 0 plus 4, and 0 minus 2. So -3, 2, 4, -2. So go ahead and graph them, and then you can tell me what kind of transformation it went. Huh?
Is it a reflection?
Over the y-axis, that's correct. Very good answer. So I'm gonna just graph it. -2, -3. So go ahead and start working on your homework, guys. Just finish this graphing while you're logging in. So this will be the end of the video. Put it over there.
That's very USC.
Oh yeah, very nice.